Okay, so we're going to do to section B now. Just make sure you read the instructions. Answer all questions in the spaces provided. Use blue or black pen. Don't use red pen. When an answer is provided in a where an answer box is provided, write your final answer in the box. If an answer box has a unit printed in it, give your answer in that unit. Don't cross it out and write your own unit. In questions where more than one mark is available, appropriate working must be shown. Okay, you will not get full marks if it's a multiple mark question and you only put an answer. Okay, unless otherwise indicated, diagrams are not drawn to scale and take the value of g to be 9.8 meters per second squared. All right. I should also mention that when you're doing your working out and you get your final answer, put your final answer in the space that's provided as well as in the box, because if for whatever reason you make a transcription error putting your answer into the box, the examiner can also see the real answer somewhere written down on the lines that are provided. Okay, and they may still award you marks for that. Okay, so just make sure you're covering all your bases so that you're making it as easy for the examiner to give you as many marks as possible. Let's begin. Question 1. 3 charges are arranged in a line as shown in figure 1. So here we've got negative charge, positive charge, negative charge. Draw an arrow at point X to show the direction of the resultant electric field at X. If the resultant electric field is 0, write the letter N at X. So let's think about what's happening here. Right, there's a point X and there are 3 charges around it. Okay, so imagine you're standing there at X and you're standing there at X, okay, and you can somehow measure the electric field. Now, let's just consider the electric field at each let's consider the electric field from each charge one at a time at point X. So from the negative charge on the left, the electric field would be pointing towards that negative charge. Okay, and we'll indicate its strength with that arrow. For the positive charge, the electric field at point X would be also pointing to the left with the same magnitude as the other one because they're equally distant from each of those charges. And now the electric field due to this negative charge on the right, that negative charge is really far away compared to the other two, but it would experience a tiny electric field towards that, like that. Okay. Now these are all vectors, and we can add vectors together by just adding the arrows tip to tail. And so there's a much stronger overall leftwards electric field than there is to the right. So we would say that overall the resultant electric field at point X would be somewhat pointing to the left, with whatever strength is there based on the strengths of the charges. So we can say that the electric field at point X points in some direction to the left. Okay. According to our examiner's report, 63% got that mark. Most common error was to state there was no field at point X, and I'm assuming that's because people probably forgot that charge was over here, and you're saying, oh look, you're exactly halfway between 2 other charges, and so they cancel out, but that's not true because the electric field from both of these charges point in the same direction. So I think it's just a misunderstanding of what was going on there. Alright, question 2. According to one model of the atom, the electron in the ground state of a hydrogen atom moves around the stationary proton in a circular orbit with a radius of 53 picometers, or 53 times 10 to the negative 12 meters. Show that the magnitude of the force acting between the proton and the electron at this separation is equal to 8.2 times 10 to the negative 8 newtons. Take K equal to this, and the magnitude of the electron and the proton charges as this. Show all steps of your working. So it's 2 marks, so it's not that many steps, I think. So it says show, let's just highlight what we're intending to do here. Show that the magnitude of the force between the proton and electron is this number here. Okay, so what do we know? We know how far they are apart. That's that number there. So that's their separation, R. We've got K. and we've got the charges of both the proton and the electron. And so we need some way to relate all of that information together. So that's Q1 and Q2. There's K. So we've got K, Q1, Q2, R, and we're trying to work out the force equals. Okay, so that's straight from your formula sheet. That's the electric force between two charges. So Q1 to Q2 over R squared times K. And that is equal to, so just write everything down, 9.0 times 10 to the 9 times, up the top we got 1.6 times 10 to the negative 19 times 1.6 times 10 to the negative 19. I'm not squaring them, even though they are the same, because I want the examiner to know that I know that there are two charges there. And on the bottom, we've got to square their separation distance. So 53 times 10 to the negative 12 squared. Okay, so if you type that on your calculator, let's see what we get. All right, so calculator, 9 times 10 to the 9 times fraction 1.6 times 10 to the negative 19 times 1.6 times 10 to the negative 19 over 53 times 10 to the negative 12 squared. I'm putting brackets there. Even though I pressed that button, I'm still putting brackets there because I don't trust my calculator. Okay, I want it to do exactly what I want it to do. All right, now it's giving me a bunch of zeros here. And one way we can fix this is I can go Shift Setup, and I can go to 6. Nope, wrong one. Go back. Oh no. Sorry, bear with me. Mode setup 8, 2, I believe it is. So if I type that all in again, sorry, skip ahead. 9 times 10 to the 9 times 1.6 times 10 to the negative 19 times 1.6 times 10 to the negative 19 over 53 times 10 to the negative 12 squared. Nope, try it again. 8, 1. There we go. Okay, so if we go Shift Setup 8 and 1, it gets rid of all those annoying zeros and puts it into scientific notation for you. Okay, so the answer is 8.2 times 10 to the negative 8. That's 2 sig figs, and that's what we're required to show. Okay, so that's that answer there. So that this line here is where you get the mark. Actually, you get 2 marks. You get 1 mark for. Let's have a look. Let's have a think. So 1 mark probably for. It's a bit hard to say here. My thinking is you probably get 1 mark taken off for each incorrect number that you put into the equation, or if you have the wrong equation itself, then that would probably take away a mark. It's a bit hard to say with show that questions where the marks are allocated, but in general it's like, okay, we'll give you 2 marks and every mistake you make will take off 1. Okay, so long as you've got the right formula with the right numbers in the right spots, those should give you 2 marks for that. Okay. Part B, using that force as the value of the magnitude of the force given in part A, calculate the speed of the electron in this circular path, take the mass of the electron to be this, show your working. Again, 3 marks, probably again for having a wrong equation with the wrong numbers put in. Alright, so what are we trying to do here? We're trying to link together the speed of the electron with the force, and it is in a circular path with this radius up here, okay, from part A, and we've got a mass of the electron as well. So let's just write things down. We've got F, we want V, it's a circular path, I've highlighted that because it's important, and we've got M, and there's also a radius of orbit up here. So we've got F, V, M, R. How do I link all these things together? Okay, and in particular, it's a circular motion question. So we go and think about what we know about circular motion, and there is a formula, F equals M V squared on R. That links all those things together. Okay, we're trying to solve for V, so you could do some algebra first or sub everything in and then do the algebra later. So I'll just rearrange now. So V equals FR over M, and then the square root of all that. Okay, now if you chuck everything in there, we've got 8.2 times 10 to the negative 8 times the orbital radius, which was given up the top. That's 53 times 10 to the negative 12. That's all over the mass, 9.1 times 10 to the negative 31. Okay, double check that we get the right answer on our calculator. So square root of fraction 8.2 times 10 to the negative 8 times 53 times 10 to the negative 12 over 9.1 times 10 to the negative 31. 218,536, blah, blah, blah. Okay, so 2.2 times 10 to the 1, 2, 3, 4, 5, 6. Okay, so 2.2 times 10 to the 6. Press engineering button to hopefully try and get us closer to where the decimal point should be. So it's 2.2 times 10 to the 6 meters per second. There you go. Question 3. Figure 2 shows a schematic diagram of a simple DC motor. Okay, I'm going to highlight motor here. All right, we are not generating, we are using electricity to create the motion, not the other way around. It consists of two magnets, a single 9-volt power supply, split ring commutator, a rectangular coil consisting of 10 loops. The total resistance of the coil is this. The length of the side JK, that's there, is this. The KL side is this length. The strength of the magnetic field is this. Okay, so highlighted all our important information. Determine the size and direction of the force acting on the side JK. And the direction is one of these options here. Okay, so this is a motor. Motor relies on having an electric current being passed through a wire that is perpendicular to magnetic field. So let's just remember what the magnetic field is doing. The magnetic field is going out of north into south, okay? And the current is going through JK. Well, let's follow the battery. So the positive terminal is here, so the current goes around like that. So the current is going that way, all right? Now, linking magnetic field, current, and force, we can use our right-hand slap rule to determine the force acting on the coil due to the current going through in the magnetic field. So you get your right hand in front of you, point your thumb, I guess, away from you because that's where the current is going. Your fingers have to point towards the right, that's the magnetic field, and your palm should be facing downwards, okay? So try that out. And that tells me that the force acting on the side of the coil JK is down. Okay. Now, what option is down? That's D. So it's in direction D. Now I just have to work out the size of the force. Okay. Now this comes from using our formula. F equals N times B times I times L, where N is the number of turns in your coil or loops, B is the magnetic field strength, I is the current in the coil, and L is the length of the piece of coil that is in the magnetic field. So that's the length of JK. So we know all those things. N is up here, 10 loops. So that's 10. B, magnetic field strength, well, that's 0.5 Tesla here. I is the current in the loop. Now, current's not given to us, but It tells us the voltage of the battery and the resistance of the wire. So we can use Ohm's law to work out the current. Ohm's law off the side, V equals IR, or I equals V over R. So the current is voltage, 9 volts, divided by the resistance, 6 ohms. And then the length of that piece of wire, JK, is 12 centimeters, which is equivalent to 0.12 meters. And if we multiply all those things together, we get, now I'm not going to do it because I don't want to waste time calculating, 0.9 newtons. Okay, cool. I think the most common error, according to our our examiner's report, students were omitting the 10 loops, so they were forgetting about the N, all right? Failing to convert your length of that piece of the coil into meters, or stating the wrong direction because you didn't know how to use your slap rule, okay? I think another thing is students were not probably aware they had to calculate the current because it wasn't given to us. Okay, so you do have to rely on your knowledge about Ohm's law for that. All right, part B. What is the size of the force acting on the side KL in the orientation shown in figure 2? Explain your answer. So if you have a look at the figure, KL is parallel to the magnetic field between your magnets. Okay, so whenever you have a current parallel to the magnetic field, there is no effect. Okay, the force on that current is nothing. All right, they have to have a perpendicular component for there to be a force. All right, so we can say that the force is 0 newtons. Okay, and you can specify there is no perpendicular component of current in the field. Okay, the examiner's report says, yep, the force is 0, so I'll chuck that in the box. Students were required to identify that the current inside KL, I'll actually get the report here so you can see what I'm talking about. Students were required to identify that the current inside KL runs parallel to the magnetic field or magnetic flux. A number of students stated that the reason was because the current was not perpendicular to the magnetic field. Students should be aware that the current does not have to be perpendicular to force exist, and that any angle between the current and field greater than 0 degrees will result in a force on the wire. So that's different to what I've said. Okay, I've said there's no perpendicular component of the current that's in the field. I've not said that it is not perpendicular. Okay, so this statement here does not apply to what I've written. My wording is basically saying it's parallel. Okay, I just haven't said the word parallel. I just said there is no perpendicular component. So I'm pretty sure that would get you the mark, okay, if they were being honest with how they mark things. But yeah, okay, so if it's parallel, there's no perpendicular component, therefore there's no force. All right. Okay, moving on to question 4. Charon, a moon of Pluto, has a circular orbit. There's a bunch of data here. Assume that Pluto is a uniform sphere. Calculate the gravitational field strength at the surface of Pluto. Show your working and include an appropriate unit. Okay, so calculate the gravitational field strength. So we want little g at the surface of Pluto. Surface of Pluto. All right. So how do I calculate gravitational field strength? Well, one formula we could use is G equals big G times mass 1, mass 2, sorry, not mass 2, I'm thinking of force. So mass of the thing exerting the gravity at some distance squared. Okay, now the fact that we're at the surface of Pluto means that this R here is simply just the radius of Pluto. Okay, so this is the R that we're using in part A. And m is the mass of Pluto. So that's what we're using in part A. All right. So now I just have to work all that out. 6.67 times 10 to the negative 11 times the mass of Pluto, 1.3 times 10 to the 22 over r squared. So again in brackets, 1.2 times 10 to the 6 meters. Oops, not meters there. Squared there. Okay, just be careful. Everything's going to be in kilograms and meters for everything to work, so that's fine. And now we just go on the calculator, type it all in. I'm not going to calculate it. The examiner's report will be able to tell us what the answer is. Okay, 0.6 newtons per kilogram. Okay, so it does also ask for a unit, include a unit. So because we're dealing with gravitational field strength, my first instinct would be to write it as newtons per kilogram. Okay, but you're not wrong to say also meters per second squared, because that's their equivalent units. Acceleration due to gravity is the same as the gravitational field strength when you think about their units and how they can be expressed as either or. Okay, so 0.6 newtons per kilogram. All right. Part B, calculate the period of orbit of Charon. Show you're working. Okay, so period of orbit. Well, we go back to your data sheet, and you should find a formula. Actually, I'll bring the data sheet up so we can see how we use it. Give me one moment. Okay, so now I've got my data sheet up. Let's have a look at what might be useful here. Now, by memory, this particular formula that I'm thinking of is not actually on here. It's sort of a combination of a couple of formulas. So I'm going to write down the formula that you should have on your data sheet that makes questions like this pretty easy. It is the following. It will be... now I'm confusing myself. Okay, let me show you how to actually derive it, and then I'll just make sure that I'm doing it properly. So this formula here for circular motion, A equals this quantity at the end. That's what I'm looking for. So A is equal to, where'd it go? 4 pi squared r over t squared. Okay, but A is also equal to acceleration due to gravity, or little g, right? So g we can also write as g times m over r squared. So I can equate those two things, get 4 pi squared r over t squared equals big G times m over r squared. I can do a little bit of rearranging now. Okay, so I can sort of chuck this r squared up here, bring the 4 pi down here, and I get r cubed over t squared equals gm over 4 pi squared. Okay, so that's a really handy formula to have on your formula sheet, or on your notes that you can bring in, because it directly relates period with a bunch of other stuff that we know. Okay. Now let's just use our data to see if we can answer this. So I want the orbital period t. So I can rearrange this algebraically to get t equals, now I'm going to have to make sure I do this properly. It's going to be the square root of 4 pi squared times r cubed over gm. Okay, I think that's right, because if I do squared divided by r cubed and then flip everything, yeah, that works. All right, cool. So now I just have to put my numbers in. Okay, 4 pi squared is 4 pi squared. Radius of Charon's orbit, so that's going up to here, 1.8 times 10 to the 7. That's cubed, so put it in brackets. And then that's all over g And m is the mass of the thing you're orbiting, which is the mass of Pluto, 1.3 times 10 to the 22. Alright, so now I've got all of that. I can now just check the answer in the solution or the report. Yep, okay, so it's 5.2 times 10 to the 5 seconds. Lovely. Okay, cool. Alright, we've been recording for 25 minutes. If you want to pause it and go have a break, and then we'll do part C. Scientists wish to place a spacecraft of mass 1,000 kilograms in an orbit of the same radius as Charon. 3 students, Rick, Melissa, and Nam, are discussing the situation and have different opinions. Rick says as the spacecraft is lighter, it will have to move at a greater speed than Charon to achieve the same orbit. Melissa says the spacecraft would need to move at the same speed as Charon. Nam says the spacecraft would need only to move at a lower speed as it is lighter than Charon. Okay, evaluate these 3 opinions. Detailed calculations are not necessary. So evaluate these 3 opinions means to look at what each of them are saying and just evaluate their claims. So is what they're saying true or false? There's not necessarily going to be a correct answer from these 3 opinions. In this case, there is a correct answer, but a question may be given to you where all of these options are wrong, and you have to explain why. Okay. Now, I am going to just look at them and, well, try and think about, well, how can we talk about the speed of an orbital body based on things we know about the orbital body. So what do we know about this spacecraft? Well, it says that it wants to be at the same orbital radius as Charon. Okay. Now, if we go up to here, actually not there, it's on the formula sheet. Okay, so the formula sheet says if you're in circular motion, then this is a true statement here. Okay, so v squared over r equals little a, but we also know little a is equal to little g, okay, when we're talking about gravity. So I can claim the following thing. Okay, because of circular motion, I can claim that v squared over r is equal to g times m over r squared. And that if I was to solve for v here, I'd get v equals the square root of gm over r. And what this equation is telling me is that the orbital speed of something that is orbiting whatever only depends on the mass of the thing we're orbiting, which in this case is Pluto, and the radius of the orbit. Okay? Now the fact that this spacecraft is to have the same orbital radius as Charon means that it should have the same orbital velocity as Charon, because this r is not changing. Okay, this r is the same for both Charon and this spacecraft. And they're both orbiting Pluto, so this m is not changing either. So the fact that m and r are not changing when we're talking about Charon or the spacecraft means that they both have the same orbital velocity. Okay. So that means Melissa is correct. They would move at the same speed. And Rick and Nam are incorrect. Okay. Now, let's just read the examiner's report. Okay. Students were required to identify that Melissa is correct and Ricky and Nam are incorrect. So we've done that. Okay. Then we have to show why. And that's us explaining that because of this circular motion, when you're orbiting Pluto, we can claim the following relationship. And then solving for v produces this equation, which tells us that, well, the velocity only depends on the mass of Pluto and the orbital radius of your object. Okay, and so it says students were required to identify that the orbital characteristics, particularly velocity of a satellite, are independent of the mass of the satellite. Okay, and that's what we're saying here. The velocity only depends on the mass of Pluto and the orbital radius at which you are orbiting. Okay. They were also required to provide some mathematical argument to support their assertion such as indicating the lack of a satellite mass in the formula v equals square root of gm over r. And that's what we've done here. I just haven't written it down. Students were not required to perform any calculations. Okay, now have a look at the marking allocations. More than 50% got 0. Many students suggested that all 3 students were correct to some extent. You can't be awarded when it's unclear whether the student has recognized an incorrect argument. Okay. Some students who were able to identify Melissa's opinion as the only correct one still had difficulty identifying why she was correct. So that's maybe where those 2 marks came from, saying like, yeah, all right, Melissa's correct, but then not expanding on that or providing an argument as to why she is correct. Okay, so hopefully my explanation is as well as this one have made you understood the answer to that one. All right, let's keep going. Question 5. The alternator, I'm going to highlight that straight away. Alternator is a generator. Make a note. Generator. The alternator in figure 3 has a rectangular coil with sides of this and 10 turns. So that is your dimensions and the number of turns. The coil rotates 4 times a second. Okay, 4 times a second. That is a frequency. How many times something happens per second. In a uniform magnetic field, the magnetic flux through the coil in the position shown is 0.2 Webers. Okay, so flux. So here we've got an, I guess, length and width, and that is an N. All right. Let's read. What do we do here? Calculate the magnitude of the magnitude of the magnetic field. Include an appropriate unit. All right. So the magnetic field and magnetic flux and a bunch of other stuff are related using this. So flux equals field strength times the area that the flux is passing through. The area that is the flux is passing through comes from these 2 numbers. Okay, so the area is 0.3 times 0.4. Actually, I'll just write my working out another line now. So we're required to work out the magnetic field strength. And so we've got B equals flux divided by area. Magnetic flux is given to us straight away, 0.2 over the area, that's 0.3 times 0.4. And so if we calculate that, we end up getting 1.7 or thereabouts. Okay. It wants a unit, so just use the most basic unit for magnetic field, that's just Tesla, so T. It is not incorrect to also put Webers per meter squared, because that's the units of field strength here. Webers for your flux, and area is meter squared, so Webers per meter squared. Right, examiner's report. Most common error was to include n equals 10 in the formula. Don't need to do that, there's no reason for us to do that. Students are reminded that the number of loops does not affect the flux calculation. Alright, cool. Let's move on. Put that back down. Alright, so calculate the magnitude of the average EMF generated in a quarter of a turn. Show all the steps of your working. Okay, average EMF. Bang, straight away, that should remind you of the average EMF formula, which we might have to use here. So it's N times change in flux over change in time. You can include a negative there, but I wouldn't, because it doesn't affect your final answer. It just makes your answer negative, which we can't state whether the EMF is negative because I don't know which direction negative is. So it doesn't make a difference here. All right, going back up to our data, we've got N equals 10 turns, so I can put that in straight away. The change in flux, now it says it's calculate the average EMF generated in a quarter of a turn. So if we look at our picture, right now it's starting at a maximum flux, but then it's going to turn and it's going to now look like that. Okay, so now the flux goes to 0. So in a quarter turn, the change in flux is just the maximum flux, because you're going from a maximum flux to 0. So the change in flux is 0.2. And it's happening in a quarter of a rotation. Okay, so let's go back to what we know about its frequency, which was up here. The coil rotates 4 times a second, so that's the frequency. Frequency is 4. So I'll just write this off the side here. F equals 4. The period, therefore, is 1 over 4, which is 0.25 seconds. And because we're talking about a quarter of a turn, the time here, delta t, is a quarter of a period. Okay? Remember, period is how long it takes to turn around once. We're talking about a quarter of a turn. So delta t is 1/4 of 0.25. Okay, so you can write that as a decimal. It's going to be 0.0625 seconds, I believe. So 0.0625. Or if you want to keep it all like the same, you can just write 1/4 of 1/4, which is 1 over 16. So you'd put 1 over 16 in your denominator, but it doesn't really make a difference here. Calculate that, and let's check the report for our answer. It's 32 volts. There you go. Okay. There you go. No further anything required here. So show all your steps. We've got all our steps. There's our formula. Putting your numbers in. Another step would be showing where you got that number, I think. Just play it safe and put that calculation on the side there. Alright, part C, figure 4 shows the output EMF versus time of the alternator for 2 complete cycles. The 2 slip rings in figure 3 are now replaced with a split ring commutator. Right, if you're skimming over questions, you may miss this step. You may miss that, that key sentence. On the axis provided below, sketch the EMF versus time graph of this new arrangement for 2 complete cycles. Okay, so just have to remember what a split ring commutator does in a generator. It makes your output from a nice sinusoidal wave to this bumpy looking wave where all the negative portions of your graph sort of flip around to become positive. Okay, so it's going to look the same. It's just now going to have no negative portions. It's all just going to bump around like this. Okay, now that's one interpretation of the graph. I would also say that an upside down version of this would also be accepted, again because there is no indication of which direction is positive or negative in this diagram, so they can't penalize you for having the same looking graph just in the negative direction instead. But I just play it safe and just keep it positive, right? Let's have a look at your examiner's report. Examiner's report says, yep, there's our graph. The inverted form of this was also acceptable, so that's what I was talking about. The most common error was to draw a biased sine wave. Not sure what they really mean by that, but probably like, I don't know, the sine wave's been moved up or down or stretched somehow. Alright, let's continue. So, question 6. Figure 5 shows a generator at an electrical power station that generates 100 megawatts RMS of power at 50 kilovolts RMS alternating current. Transformer T1 steps the voltage up to 500 kilovolts RMS for transmission through transmission wires that have a total resistance of this. Transformer T2 steps the voltage down to 50 kilovolts at the substation here. Assume that both transformers are ideal. So let's highlight our numbers. It's power. That's the voltage on the left-hand side of the first transformer. That's the voltage on the right-hand side of the first transformer. Resistance of our power lines. That is the voltage on the right-hand side of the second transformer. Okay, and all that information is drawn again in your diagram. The current in the transmission lines is 200 amps, and that means here, 200 amps here. Calculate the total power loss in the transmission wires. Okay, so it's just asking for power loss. Okay, power loss formula is I squared times R. We know I is 200. We know the total resistance, that's up there in the question here. That's 3 ohms. 200 squared times 3. Can't be bothered thinking. Let's look at the answer. There we go. 1.2 times 10 to the 5 watts. But look at what the units are in the box. It wants it in kilowatts. Okay, so if I write this out in total, that's the same as 120,000 with a decimal point there. All right, and that kilowatts would be moving the decimal point to here and looking at this number on the left. So that's 120 kilowatts. Okay, or another way to think about it is if you put this on the calculator. So let's show you how to set this up. 200 squared times 3 will give you this. Press engineering button. Every time you press it, the power of 10 goes up by 3. And times 10 to the 3 is kilo. So the answer is 120 kilowatts. Okay, so just a handy hint there. Examiner's report says most common error was incorrectly converting to kilowatts. Well, there you go. Okay, make sure you read the answer in the box. Make sure you know how to use your calculator to get that kilo on there. Transformer T1 stepped the voltage up to 250 kilovolts RMS AC instead of 500 kilovolts RMS. By what factor would the power loss in the transmission lines increase? All right, let's think about this. So what it's saying is the transformer, instead of stepping up to 500 kilovolts, it steps it up to only 250 kilovolts. Okay. Now, according to our transformer equation, okay, actually, I don't even think you need to use a transformer equation here. I think we could just talk about it in terms of power. So, power on the left-hand side of this transformer. Let's look at that. Power on the left-hand side is 100 megawatts, so 100 times 10 to the 6 times, by the way, I'm using P equals IV, P equals VI, times, hang on, I don't have the current, okay, so maybe that's not the way I need to think about this. No, actually, I can do it this way, okay, so if I use P equals VI, let's look at the right-hand side of the transformer. What's happening on the right? Well, the power we know, if it's an ideal transformer, then the power on the right-hand side of the transformer is still 100 megawatts. Okay, there's no power loss right after we step it up. Okay, so I've got 100 million watts. That equals my voltage, which is now 250. Okay, instead of 500. So, 250 kilovolts times 10 to the 6 times 10 to the 3. And that produces some new current, right? So what's the value of this new current that's being produced? Well, that's going to be 100 times 10 to the 6 over 250 times 10 to the 3. Okay? And that's going to be, I think, 400. Okay? So the new current produced here is 400 amps. Comparing that to the original current of 200 amps, how does my power loss now compare? So my power loss with this new current is 400 squared, so current squared times resistance, which is 480 kilowatts. Okay? And so, by what factor would the power loss in the transmission lines increase? That means there's a factor of 4. Because I've gone from 120 kilowatts to 480. It's multiplied by 4 to get this new power loss. Okay? So just shove a 4 in here. let's have a read of your examiner's report. Okay, so the current doubles, that's what our calculation here showed us. Now using that new current in your power loss formula, you get this number here. And again, comparing that number to the original power loss, that's an increase by a factor of 4. Okay. Many students were unable to find the new current. A number of students who found the new current reported the power loss rather than the factor. So they wrote the power loss number in here. Just make sure you read the question. What does it actually want you to write down as your answer? Okay. All right, let's move on. Question 7. A bicycle and its rider have a total mass of 100 kilograms and travel around a circular banked track at a radius of 20 meters and a constant speed of 10 meters per second as shown in figure 6. The track is banked so that there is no sideways friction. That's very important, so I'm going to highlight that. Applied by the track on the wheels. Okay. A. On the diagram below, draw all of the forces on the rider and the bicycle considered as a single object as arrows. Draw the resultant force as a dashed arrow labeled F net. Okay, so let's think about the forces acting on this bicycle rider. Obviously, if you're on Earth, there's gravity, so we'll point gravity down. We'll label it as Fg. There is also a contact force, or a normal force, between the wheels of the bike and the surface. So we can draw a normal force at the point of contact, but perpendicular to the point of contact. So that's your normal force. And there's no friction or anything, so those are the only two forces that are doing anything. Now, what is the resultant force? Well, that's just me adding the forces together as vectors. So that's got the normal force pointing up like that, plus gravity like that. Your resultant force is that way, okay? And you should already kind of know that because we're talking about being in a circular path. Okay, the bike rider is going around in a circle, which means the net force has to be pointing towards the center of the circle, which is somewhere over here. Okay, so the net force is looking like that, and we label it F net. Okay. All right. Let's look at the examiner report quickly. So there we go. There we go. There's our normal force, our gravity force, and the net force. Pretty well done question, I'd say. Most common errors were the inclusion of extra forces or drawing F net as down the slope. Now that's a very common thing, drawing F net down the slope. That's only true if you're just like sitting on the slope, not moving, or you might be just going down the slope, like a sliding down or rolling down the slope. This is a banked track, and you're not moving down like this. You are going around in a circle. Okay, so it's a completely different scenario. The net force would only be down the slope if you were accelerating down the slope, like a ball rolling down a hill. Yeah. All right. Part B. Calculate the correct angle of bank for there to be no sideways friction applied by the track on the wheels. Show your working. Okay. Now, there is a formula that just calculates this straight away, and that formula is tan theta equals, oh, now it eludes me what it is. It might be in the formula sheet. Let me see if I can derive it. No, okay, see, I'm trying to do this without my own notes, my own formula sheet, so forgive me if I have to think a little bit here. Okay, let me pause 1 second, I'll get back to you, hang on. Okay, so I remember it now. The formula is G tan theta equals V squared on R. Okay. And by rearranging this, we end up getting theta equals tan inverse of V squared over GR. Alright. Now, by subbing stuff in, we've got some things up here. So we have the mass, we have the speed, and we have the radius of the track there as 20 meters. We don't actually need the mass in this formula, so it's just the v squared over gr, and then inverse tan of all that. So tan inverse of speed was 10 over 9.8 times 20, and we end up getting, let's have a look at the examiner's report. There we go, 27 degrees or thereabouts. Oops. Something happened on my end. There we go. All right, so about 27 degrees. All right. Yeah, it's worthwhile going back into the notes to see where this comes from. Okay, just slipped my mind for a second, but yeah, we've got a way to set this up on your banked track. It's just to do with how the vectors of the forces interact with one another. This is a very useful formula to have on your cheat sheet. Okay, so write this one down and write it down to say that this applies when you have an object going around a circular banked track. Okay, at design speed. Okay, that's a very specific speed that it needs to be traveling at. So design speed, that is the speed at which there is no sideways friction applied by the track on your object. Okay, so have that on your cheat sheet if you don't have it already. All right, I might do this last question, just this last page, and then I'm going to pause, make a new video. So let's keep going. A roller coaster is arranged so that the normal reaction force on the rider in a car at the top of the circular arc at point P, shown in figure 7, is briefly 0. So make a note there, briefly 0 at the point where it is. The section of track at point P has a radius of 6.4 meters. All right. Calculate the speed that the car needs to have to achieve a 0 normal reaction force on the rider at point P. Now, I'm not going to go into where this formula is coming from. Go back to the notes and read through the notes and then write this formula down on your cheat sheet, okay? But basically, for there to be 0 normal force at the top here, okay, all of the force that's acting on your rider at that point is going to be just gravity, okay? Because really, I mean, if you were going up there, you'd have a normal force pointing up, you'd have gravity pointing down, but the net force would still have to be down because that's where the center of your circular path is, okay? But if the normal force is 0, that's missing, all right? And you simply have gravity causing you to go in a circular path. And so your formula would be mg equals mv squared on r, and so the m's cancel out, and you get g equals v squared on r, all right? And so we're solving for v. So v, yeah, calculate the speed. So v equals square root of gr. Okay, square root of gr, square root of 9.8 times the radius, 6.4. That's equal to, let's have a look at your report, 7.9 meters per second. Okay. So go back and review these scenarios where you've got like a circular path going on top of a hill, stuff like that. The car is faulty and only achieves a speed of 4 meters per second at the top of the arc at point P. Calculate how fast this car would be moving when it reaches the bottom at point Q, 5 meters below point P, assuming that there is no friction and no driving force on the car. So for this question, we need to use conservation of energy. So right up here, they have kinetic energy plus gravitational potential energy. Down here, they have only kinetic energy. Okay? And using that, our value for kinetic energy, we can then solve for how fast it's traveling at that point. So at the top of the circular arc, the energy, so at the top, or at point P, energy equals half mv squared, that's kinetic energy, plus mg delta h, that's gravitational potential energy. So if I sub all my numbers in, I get half times the mass of the car, which is where's Where's the mass? Maybe I don't have to use the mass. I don't have to use the mass, and I'll show you why. Okay, so at the top, point P, I'm not going to write equals there, I'll just leave it like that. Okay, at point P, that's the total energy. Okay, and I'll use subscript 1 for the velocity at that point. Okay, at point Q, the total energy is equal to half mv2 squared. Okay, that's the velocity that it's got there. Okay, but all of the gravitational potential energy has been converted into kinetic energy at that point. Okay, and because the total energy between this interaction has to be equal, I can set these E's equal to each other. Okay, so I have half mv1 squared plus mg delta h equals half mv2 squared. Now, because we've got m's in each of the terms on both sides of the equal sign, they can just cross out. They disappear because I can factor them out and then just divide both sides by 1 over m, or multiply both sides by 1 over m, and they just go away. All right, so now I just need to solve for v2. So v2 is equal to, I'll keep it as half v2 squared for now. That's equal to half v squared, v1 squared, plus g times delta h. Okay, and so v2, so multiply everything by 2 on the other side and then take a square root. It's going to be v1 squared plus 2g delta h equals the square root of, okay, what's the speed at the top of the hump? It's 4. So 4 squared plus 2 times 9.8 times what's the change in height? That was 5 meters. So that's times 5. And we end up getting, can't do that in my head. Let's just look at the answer. Okay, 10.7 apparently. Cool. 10.7 meters per second. Done. All right, quick look at the examiner's report, then I'm going to cut this and make another video. Right, so they basically did what I thought about doing. So I know that the energies at the 2 points are equal. The energy at the top is kinetic plus gravitational. The energy at the bottom is just kinetic, but they have 2 different speeds at those points. So we equate them. Notice that the m's can cancel out, and then we're left with another equation, which we then solve for v2. The most common error was to ignore the initial kinetic energy and simply convert the gravitational potential energy to kinetic energy. So yeah, some people just said, they're not moving, so whatever gravitational potential energy they lost in that interaction was then the final kinetic energy at that point, and then they solved for v that way. But they ignored that it still had kinetic energy at this point, so we had to add that in to our final answer there. Okay. All right, we'll stop it there, and then I'm going to cut this and make the next video. So probably one more video, and then that's going to be it for the 2017 exam.